All right. So I was given the instruction that we should assume basic level introduction, and I realized that we've been talking a lot about the algorithms, but there's no implementation. So I figured it might be just one good strategy just to at least try to implement something and see how it goes. So my plan is that I'm going to give you a very short introduction on the library that we've been building, and sort of tell you the design and how it differentiates from current available libraries. So if you're interested in looking at code, it's C++ based, but it's not as sophisticated as C++ as Ian's code, or it's more like an iTensor level C++. Okay, so if you click, and then we'll bring you to and this is some introduction. So all the source code are on GitHub. So basically, I mean, been seeing a lot of this graphical representation of tensors. Okay. And we know that the tensor networks basically are built on top of this. You can draw your tensor network diagrams. Okay. So just imagine that your advisor wants you to program a 2D mirror. So for people who have no idea what 2D mirror is,
I would just say no.
This is 2D mirror. Okay. So it looks very simple, right? Right? Or even just program a 1D mirror. Okay. My experience is that if you start from scratch, it might take you a year to make this working. Just debugging all this, make all the indexes are connected properly. And this one, I don't know. I think there's only very few people in this audience that have experienced 2D mirror, Arada-san and Philip. Anybody else? Oh yeah, Luca. So, and if you want to put fermions on it, so you have to be careful that when you swap to fermions, then there's a minus sign. Okay? So basically, we started programming Mera, and my student got very frustrated, and he decided to build a library. Okay, so this is where this intent comes from. So currently, there are some. We want to program these algorithms. Okay, and you can use your favorite program language. A lot of people use MATLAB. Some people use C++. You can do it in Fortran, no problem. Recently, it's Python, and I think some people are trying to use Julia, and I'm not really familiar with that language. But at the end, if you want to do a large calculation, you want to interface with some low-level libraries, say BLAS, LAPACK. We use a lot of GPU stuff, and we want to interface them. So basically, it's just you have to do this, okay? And our goal is we provide you something, so it's sort of like a middleware, and makes this programming easy. And so there's a lot of tensor library available. I think a lot of people use NCOM or SCOM, and there's a local MP tensor, and there's a TNT, this tensor network. I forgot what's T. A token. Yeah, and iTensor, of course, is mine also is iTensor. So, I think I don't know about TNT because I only browse their website, but I think our goal is that we want to our aim is mTOR applications of tensor network algorithm, especially the higher dimensional ones. So make life easy for people to program, and we provide wrappers for Python and maybe MATLAB, but we don't have the manpower to write MATLAB wrapper. And we have an in-house version of a GPU version, and we are cleaning up the code, so we want to push to the repo very soon. And you are welcome to use it. So so the design of this library is actually composed. The main character is the unit tensor, and so we have some auxiliary classes. So basically, this is the quantum number. So far we have a U1 quantum number and two Z2 quantum number, and you can use this quantum number to build bonds. So these are bonds. Okay. And so basically, it's easy just to get this multiplicity, and the symmetric tensor will be block diagonal, so you can take out them and do operation and do truncation. And slightly different from other tensor network libraries, that we have this network higher level operations. So basically, yeah, I'm gonna describe it. So let's talk about symmetry. So if I want to write down the two-side Hamiltonian for spin 1 Heisenberg model, so this will be my tensor. Okay, so this and these are all physical legs. So for each leg, I'll have this basis. Okay, but just imagine that you want to construct a symmetric basis. So this is normally how we write this. So basically, this is just a product basis. Okay, so this will be up, up, and up 0, and so on. Okay. And so this is easy to write because we know how to put this matrix element. But normally, this is what we want. Okay, we want it to become a block diagonal. Okay. So in this library, this basic is done automatically. Just fill in the tensor, the matrix in the product basis, and all this will be, it actually be stored this way. And, yeah. So the operation is easy. So you just add labels to what kind of to each bound of the tensor, and the repeated labels will be contracted. So this tensor contraction is basically just TA times TB. And so there's a list of operations, this permutation and all that. So currently we only have one U1 symmetry, but we're in the process of putting like multiple for U1. Just our symmetry class was not designed properly initially. And we have a parity symmetry and Z2 fermion symmetry. And so fermion actually, what? Okay, questions? So basically, the fermion parity is taken care of automatically. So when you do a contraction, okay, you don't have to worry about like where to put this the minus sign. So the computer will automatically put the proper swap gate at the so basically we'll change the matrix element. Yeah. So last thing I want to talk about is this network class. So basically, you see this very complicated network, and if you want to contract them, so basically you need to know the proper labels, proper dimensions, and all that. So we have a slightly higher level operation. So basically, you can just describe your network, how these bonds are, how these tensors are connected, and through these bonds, through these labels. Okay. So basically, this will describe this kind of network. Okay. So this and all you need to do is just put in the tensors. Okay. And the library will automatically check if the label, so for example, check if the labels are right, if the bonds are right, if this is contractible. And so after you fill in all the tensors, then it just does a contraction for you, and then will be the final tensor. And you can replace it. A lot of times you just want to recontract the whole thing, but you want to leave the rest. untouched. So you can replace one tensor and do the contraction. One thing is that the library has a heuristic algorithm, basically just to determine what's the optimal contraction order. So, but we're gonna implement this. Okay. So basically, we try to break the contraction into binary contraction trees, and with some criterion. So it's detail. Yeah. So we basically try to build a contraction tree based on the given order. Okay, and try to locally optimize. Yeah.
Can you force the library to do the sequence that you?
Yes. So you can basically just use say this is the, you just use the brackets.
Okay.
Okay, and then you just force the library to contract. If you already know the best option. So this is so the whole the file is parsed, and also for fermionic system, one tricky thing is that the best contraction order, the sign might not be the same as the way you want to contract it. Okay, but this is taken care of, and so it should work. We tested in some very simple cases, but we didn't test a very complicated case, but it seems to work. Okay. Yeah. So just to give you some examples. Okay. So this is a part of the mirror operation. So this is a ascending operator. It basically is the remodelation of a two-side operator, say two-side Hamiltonian. Okay, and you want to contract this to get this. So this is a C++ sample. Okay. So all I need to do is just I can define some quantum numbers. So these are the quantum numbers. So I can have fermion parity even, and this is U1 charge 1, and this is parity even, Z2 parity even. And I can define fermion parity off. So these are the quantum numbers I have in the and then I collect them. I can define a bound. So there are two types of bounds. So it's an in bound or out bound. So there's directional, and so we store actually all the tensors in matrix. So they will correspond to the column and the row of the underlying matrix. And then
is it only for mirror? I mean,
no, for all the tensors are stored in matrix, because then we can take it. You can use +3. So we define the bounds, the type of the bound, and what quantum numbers are carried. This bound carries. Okay, so there will be list bounds, say Q1 and Q-1, for example, and then collect all the bounds. Then I can define a Hamiltonian. Okay, so I define a tensor. I put into the matrix element. And this Hamiltonian is defined in terms of this box. I can give it a label. Okay. So this is a defined Hamiltonian, and we can, in the same way, defining W and W dagger. And all these pushbacks are because this was C++ 99 or something. Now you can use just a curly bracket just to initialize this. So it will become shorter. Okay. And the final thing is that after you got all these tensors, we just you just load this tensor, this network file, and put the tensors into this network, and then provide just issue this command launch, and just construct for you. So this is the network file. Yeah. So in less than 100 line of C++ code, you can write this ascending. And basically, there's only 3 ascending operators. If you do a ternary mirror, right? So I can show.
Actual 100 lines or Frank Pullman?
It's really hard. Well, I'm going to show you. I'm going to show you 1D mirror, what my student wrote. Okay. So this is so the full mirror. So this is the main implementation. Okay. So if you can see the lines here, that's for one function. It's less than 100 line. But here it's like 300 lines. Okay. And I think we can ask Harada-san. Can you do so? All the auxiliary and the main functions probably less than 1,000 lines, and it works. And it's easy to add symmetry. Okay, so yeah, so you are welcome to try it out. So that's and since we don't have much access to supercomputer that often, so we try to accelerate using GPUs, graphic cards. And this is the old data, so I didn't update it. It depends on the cases. We didn't really optimize the GPU. We just used cuPlus and didn't really do a very nice optimization. So I think we can get the per socket 30 to 40 speed up. Depends on the type of problem. I think Mera we get the biggest speed up, okay, because there's a lot of contraction. So yeah, so we should acknowledge our maintainer, and let's develop this me and Po Zhongshen. He's not here. He's not supporting the team. And there's a student. So he's taking over, so it's going to finish in 1 year. So we need a lot of help. So please focus on GitHub. So my idea is that I want to make this sort of like community-based code, and we can have something that people work together, and not everybody has to start from scratch. Okay, so this is the GitHub push. So this student, after this practice, he decided he doesn't want to do a PhD. He goes to industry directly, and he's making a lot of money. Okay. And if you look at the number of lines changes, I'm the key developer. Okay, so let me summarize. Okay. So the idea is that this is geared toward tensor network algorithm. So we have this higher level structure that makes programming higher dimensional things easier. And the hope is that we will keep our API fixed, so you don't really need to know too much about the behind the scene optimization. But you can also do it yourself because the source code is available. So what we are doing now is that we want to have a GUI. Basically, just you can drag and just connect the shapes and generate a network file, and then because in this business, basically, you know how to draw the diagram, you know how to do the tensor network. Another thing is we will want to improve our symmetry class, and we hope we can do non-obvious symmetries, but it's all, yeah, we will rely on Ian's expertise. And yeah, so we'll be better. We hope that we can scale it, okay, but we don't have the expertise to here. And also, we're going to implement the contraction search in NCOM. So we'll be maybe the contraction will be much faster. And we're rewriting the Python interface. So today, the Python that we introduced is automatically generated. But last night I found there are some serious bugs we could not really fill fixed in this framework. So we're going to rewrite this using Cython. Yeah. So, okay. So any questions about this part? So please focus and just pull request. Okay. So so I'm just gonna go through these tutorials, and I hope at least some people install the PyUnit and runs successfully. If you are using Linux, there should be a problem. If you're using Apple, there might be some issues with the path. If you're using Windows, okay, there's no guarantee. So there's a Windows build. I hope it works, but I didn't extensively test it. So if you install the PyUnit 10, then all you need to do in Python is just import it. So the basic idea to use this library is you start from the smallest thing. So you start with the quantum number. Okay. So I use this to define a quantum number object. So this, without assigning any parameters, this just give me a U1 symmetry. This is basically symmetric quantum numbers. It's just U1 charge 0, parity 0, and it's fermion 0. And then just take these quantum numbers, so you can define a bound. So for example, I can put this quantum numbers in a list, and then I define this bound. I want to call it this in bound. Okay. So and this bound carries this 3 quantum number with charge 0. So there's 3 states with charge 0. So I define a bound called BI, and this is the bound. So it's an in bound. These are the quantum numbers. This is the degeneracy, and the dimension is 3. Okay, and we're not going to use symmetry in this first part of the tutorial. So we can use just say I define a dimensional 3 bound, and then I do the same thing. Okay. So now I have bounds, right? I define the states I want to carry on each bound. So I can use these bounds to define a tensor. So if there's no bound information, so this just means it's a scalar. So this gives you a scalar. And so this just and all these tensors elements are initialized. So by default, they are all initialized. So it's all set to 0. It might give you some, might cause some speed, but I think it's probably safer this way. So to define a rank 1 tensor, okay, so the rank 1 tensor, there's only one bound. So I supply a list of only one bound. So this is a unit tensor with a list with a single bound, and this bound carries has 3 states, okay, and these 3 charge 0 states. And we provide this kind of ASCII diagram. So if you want to print, you'll show your tensor is you have one in bound, your vector is one in bound, and this is the label. Sorry, this is the dimension, and this is the label. So if you don't assign a label, the label will be given by automatically. So get information about the bounds, and we'll get information about the symmetry blocks. So in this case, there's only one block, so it's 3 by 3 block, 3 by 1 block. And we can use the same way define a rank 2 tensor. So this rank 2 tensor, so I want an inbound and one outbound. So this is a rank 3 tensor. A rank 2 tensor, so basically it's a matrix. Okay. So this inbound will be column, this will be row. And the way I define this is that the inbound is 3 dimension, the dimension is 4, and these are the labels. And we provide some helper functions, some methods. For example, just try to randomize, and we'll give you a random elements. So now the question is that I use inbound and outbound. So if I put both inbounds, what would the shape of the network of the tensor look like? Okay. So this is the shape of. So basically, it's just it's a vector. Okay. So but you can still assign different bounds, but this block is a 9 by 1 block. So just by defining bound direction, okay. So this BO is a outbound. So basically, it's sort of like it's sort of like where you put your indices. Okay. So I define a different. Now I have two. Now okay. So now I can use this same scheme define some tensors. Okay. So this is this tensor label 0 and 1, and this 3, 4 dimension, and another tensor is 3, 4, and 0 and 1. So remember that we override this multiplication to contraction. So if I want to contract these two objects, I need to assign new labels. So if I want to contract this leg, I need to assign new labels. So I set there's a function called a set label. So I just set label. So this bound becomes a label. This bound label becomes 1 and 2. So then I can contract. Okay. Set label. So the repeated label will be contracted. So. Okay. So we can try to do say. Since this is a column and row, so if I want to contract m times n, I should get an error. No. So n times n. Okay. I was expecting an error, but no. So you should have if you just take it and run it initially, you should have an error on this n times m, because the repeat index are not compatible. Okay, so this label, the dimension is 4, and this label dimension is 3. So it's not, you cannot contract these two. So that's why there's a runtime error, because the check the contraction and it doesn't work. So the way to do it is to set the proper label and then contract them, and you get the right dimensions. And there's some other things that a lot of times you need to take the tensor product of two tensors. So this can be done. It's old times. And a lot of times we want to do a permutation. So this permute is basically permute the bounds 0, 1, 2, 3 to 1, 3, 2, 0. So just take the original label and permute them. Okay, and I want to keep two in bounds. So after the permutation, this is what I get. Okay, so this is compared to this figure here. Okay.
If you apply this swapping, then actual swapping of the data occurs, or is it just changing some labels, or actual data do not move, or?
So if you just do this permute on a tensor level, it's nothing changes.
Mm-hmm.
Okay, only when inside the network you have a reference state, then we'll put the swap gate.
Okay, so
in the
you
proper place.
basically don't touch the
The
matrices.
yes.
Ma'am,
Yeah.
so what's the order of the forms for the resulting tensor after construction?
Second?
So what's the order of the hub?
Oh, okay. I understand. So if there's certain way that you can assign this output order. So in the contraction, you can say, okay, I want to fold one leg to the out leg, so I can do the next operation. So it's possible, but if you don't assign anything, all the legs remain in their original order. Okay. So this is the boring part. So let's try to implement ITBD. So this is okay. So we import pi unit 10, and since we're gonna plot something, we just import all the necessary modules. And so this is just a setup. So we want to construct the Hamiltonian for this transverse IC model, and we need operators. So we need a sigma plus, sigma minus, and sigma z. So this is how we construct the operators. Okay. So so this is spin 1/2. So this is my dimension. So I just give the matrix some dimension, and what's the matrix element? Okay, in the proper order. So this order is all in C order. And so this S plus, S minus, SZ. So we can use this. Sorry, this should be sigma. Oh no, this is S. Sorry. So we can use these matrices. Right? For example, I want to construct a Sx. So I just take the S plus, S minus, and divide by 2. So this will give my. And we need to construct. Okay, we need to construct this two-side operator. So we want to put, because in ITBD you have a two-side gate, so you want to write everything in the two-side operator. So how do you do this sigma z cross sigma z? So basically just do this remember I just introduced you have O times, so it can tensor product to tensors or tensor product to matrices. So this is just tensor product to matrices, and construct here. So here just identity times Sx, sigma s, and sigma x times identity. So then we have a two-side operator using the single-side operator. And then we just define bounds and we define our tensor, this Hamiltonian tensor, with two inbound and two outbound, and we can give it a label. And then we just put the matrix element. We can put a block, so this is the matrix, we just put the matrix element directly into this tensor. Okay. Maybe I should go back to the tutorial. So I should do this first. Okay, so the idea is that we want to update a matrix product state. We want to update a matrix product state, an infinite matrix product state. So I have this Hamiltonian. So the idea is that I want to get a ground state Hamiltonian, just apply this gate. And we do it with imaginary time evolution. So to perform this update, we decompose them into using Suzuki product decomposition, and decompose them into two types of bounds. So it will be two-side operator is either acting on AB, 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 or BA, BA, BA. So the idea is that we update this tensor by applying this, and then this, and keep going, and we do the time evolution. So in this tutorial, we're going to use the simplest type of ITBD. So basically, you take this tensor, a region in the canonical form, apply this gate. So you get a big fat tensor, and do a SVD. And then this singular value is updated, and then you make it back the proper canonical form. So this method, there's some inverse of the singular value involved, so it's unstable. It might be unstable numerically, but this is easy to understand. Okay. So look at so basically this code just try to implement this. So we have the Hamiltonian. And so basically these two functions are just some helper functions, because we have we have this tensor, and we need to combine them. Okay, we need to combine this diagonal singular value into this tensor and contract, and then do some operations. So these two helper functions are basically doing these things. Okay. So basically just contract the tensor with this lambda, and remove the lambda. Okay. So with this, now I'm ready to define my operators. So I first get my Hamiltonian. So these are this is the bound dimension I want. N is the number of iterations, and delta is this trotter step. So here's the code. So again, I define bounds define in bounds and out bounds. So I define these tensors. I have two tensors, the gamma A, gamma B. Right. So basically, I just define these unit tensors. So this tensor is a three-leg tensor. So has one bound, incoming bound, outgoing bound, and we just take one bound from the Hamiltonian. So this is just to make sure that when I connect these two, the dimension will be right. Okay, so this is some trick that we use. And we initialize these bonds, initialize these tensors, and we also define the lambda matrices. Okay, and then we set out this unitary operator. So this is a little bit hard to understand, but since we use this exponential operator so frequently, we basically have for the tensor we have this we can raise the exponential, right? So make life slightly easier and get the matrix. So this is my gamma A tensor. Okay, so it doesn't look like what we used to the MPS form, but just imagine one of the layers coming down. And this is gamma 2, and this is our lambda. Okay, so we don't have vector in our library, but we have this so-called diagonal tensor. Okay. So the good thing about this diagonal tensor is that when you try to contract lambda and the tensor, it's just a tensor operation. It's a matrix operation. So these are the updates here. So I do it iteratively. So I choose A and B matrix tensors. So alternatively. And so I get all these bonds and set labels so that I can contract with my unitary my time evolution operator, and then with all this I just contract them. So this contract so this basically just says you put this together and contract them. Okay, and yeah, we're gonna permute some. After we got this, we permute it into some label, and then we do SVD, and then after SVD, we'll do truncation. Okay, so this part is just a truncation, and then keep going. So let me. So about this Python wrapper, the good thing is that although you are programming in Python, so actually it calls the C library directly, so you don't suffer from because iteration in Python is terrible, it's very slow, and all this computation is basically wrapped to BLAS and LAPACK. So, but the good thing about Python is that you can just take the data and plot it directly. Okay, so this is the convergence. Okay, so this is a 1.2 transverse field. So, any questions? I'm not sure this way it works. So maybe let me just showcase a little bit how to use the symmetry. Okay. So if you want to think about the global symmetry, so okay, we heard about this local symmetries this morning, but let's just think about the global symmetry for the moment. So the symmetry So what does it mean that a tensor is symmetric under some group operation? So in general, a symmetric tensor, you can think of something like this. So this is a vector. So a symmetric vector just means that you do some transformation and it's invariant. And so same way for this matrix, you do some transformation and it's symmetric. And the same way for a rank 3 tensor. Okay. So for U1 case, then you need to define a direction, okay, because this is how you define the sign of your charge. And all the symmetric tensor just basically says say if I have a U1 symmetry, so number of incoming charge, the total incoming charge will be the same as the outgoing charge. So this is what it means by symmetry. Okay, so all the incoming charges are the same as the total outgoing charges. Okay, and then use this idea, you can define say a U1 symmetric tensor network. So you have a tensor network. Okay, so these are the internal legs. You have a tensor network, okay, with these external bounds. So you apply the symmetry operations on these external bounds. And since if these tensors are symmetric, you can add one. So this is W dagger W. So it's just 2 unitaries. And using this tensor symmetry condition, so you get an invariant tensor network. Okay, so this is the idea. So in principle, this can be also not any group element. Okay. So the way we define the tensor in unit 10 is basically because the tensor is stored as a matrix, so it will be just a block diagonal with different quantum numbers. So there's so for this purpose, there's if you want to define a symmetric tensor, I can just I define quantum numbers. Okay, so there's some getter functions to get what kind of this quantum number is in this sorry, what kind of U1 charge? What's the charge for parity in this quantum number object? Okay. So let's look at the. So let's look at the same Hamiltonian, but spin one half Hamiltonian in the U1 symmetric fashion.
Works for me.
It's weird. Because it works last night, so.
Yeah, yeah, it's working for me. I just don't want it now. It's fine.
Mm, So you use Linux, right?
Yeah. Do you want to borrow my laptop?
Hmm?
Do you want to borrow my laptop?
Yeah, sorry, I apologize. I thought. Let's recompile it. Hopefully it works. Okay. I don't know what happened. I just downloaded because I want to check, I downloaded the PyUnit 10. It should be the same thing, I don't know. Okay, so, yeah. So in the future, we hope we can put this on using pip install, then it will be less troublesome. I don't know. Okay, so yeah, it works now. So this is my Heisenberg Hamiltonian. Okay, so this is already. We put this matrix. Okay, we put this matrix. So this is a set row element. So I just basically take from this Heisenberg model, get a block and some pointer and put it in. The detail is not that important. We're going to write some idioms so that people can just copy and paste. So this is my U1 Hamiltonian. Okay. So look at here. I basically did nothing. I just assigned quantum numbers in my legs, in my bonds, and then I just throw in this matrix. But with that, I get the information about of this diagonal, this block, right? I have a block which is 0, 0, and then I have a spin 0 block and this spin 2 block. Spin 1 block. Okay. So this is my U1 Hamiltonian. Okay, so I look at my Hamiltonian, I know that, so my block will have these U1 charges. Well, U1 charge is -2, 2, 0. So I didn't define these quantum numbers, I just define them. And the reason why I want to do this, because I can just take out this block directly and put it into a matrix. Okay, so this is the matrix. Okay, so I just take out the Q0 block. Okay, and then this is the 2x2 matrix. So it's actually very easy just to take out the symmetric blocks. Okay, and you can take out a list of blocks. So I take out the Q2 block, so it's just one element, and this Q minus 2 block is just another element. And there's a lot of bound operation we can do. So I can combine these bounds. So a lot of in tensor network, a lot of times you have to combine the bounds, but you want to keep these bounds information separate. So you just want to make it. For example, you want to what do you want to do? So you contract to MPO, MPS and MPO, then you have a very big leg, okay, and you want to do SVD. And then what you can do is combine bonds and do SVD, and then separate them. And the library will keep track of the memory location, so you don't have to worry about where to put your elements. Okay. Another issue is, okay, so this is some trick. Another issue is that since these are all symmetric tensors, they shouldn't carry net quantum number. But if you think about this, S plus and S minus individually is not a symmetric tensor or symmetric. But S plus, S minus is U1 symmetric. Okay, so there are several ways to fix it, but the way we found is that we just construct a non-symmetric operator. So then we don't have to conserve anything. So I construct a 2x2 matrix without the symmetry, and then use that to construct a symmetric tensor. Okay. And since if the operation is done properly, then only the symmetric blocks will have elements, and that's really what we need. But I think there's a more general way to construct this type of operators. You can add a fictitious bound, and that bound carries the quantum number. So that's be important if you want to create some excitations, you want to measure some correlations. But anyway. Okay. Yeah. So with this I can use this all times. So this is a tensor outer product to get all these operators I want. And then I can use these operators to construct my Hamiltonian. So any questions?
I wonder how you are going to introduce the upper bound or lower bound maybe for the quantum numbers.
Currently, we are very modest, so basically just minus 1,000 to 1,000.
Oh, I see.
It's hard-coded,
Oh.
but we hope that we can change such that you can set yourself, because the current type is a long integer. So,
I see.
so that's just for convenience. We just hard-coded everything. Can be because so we are rewriting the symmetry class so that well probably just you can have a limit just long integer, maybe half of a long integer so that you don't get overflow. Yeah, and then all these Zn symmetries can be modulo of this pseudo U1.
Oh.
So with this U1 Hamiltonian, then I can perform ITBD, but with the U1 symmetry. So almost all the things are the same. Yeah, the only thing that you have to worry about is that since you basically your operators and tensors are block diagonal. So how do you truncate after? How do you do the SVD properly? Okay. So you have to. So either you set the criterion, okay, where to cut, and then compare in each block to just define like in each block what's the bound dimension you want to keep. Okay. I think this is the tricky part when you have a symmetric tensor. So this is the most difficult part in all these algorithms. Okay. So let me just draw this. So as long as you figure out this, because then all this you don't really need to worry if your bounds are carries the right quantum numbers, and then the contraction will be the right will be done properly. So it'll be each block you'll generate the proper quantum numbers. So you see that the contraction actually is almost the same as before. Yeah, it's almost the same as before. So the only tricky part is this SVD truncation. So this is the only tricky part. Now you have a U1 symmetric ITBD. Questions?
I wonder why do you increase this set truncation function in your library? And truncation is very general procedure. So why do you support this?
Oh no, this is not in the not in the library. This is you have to define the extra because there's
why don't you include it in your
Standard.
I think we thought about it. So I think one of the design decisions we have to make is that currently our classes are too fast. So if I show you the source code, so this matrix class probably have like it's more than 30 methods, and it becomes a little bit too difficult to maintain. So our idea is that we will write some idioms. So we have another repo. So this is the template for ITBD, U1 ITBD, and then this code will go in with proper comments, and then so this is like a boilerplate thing that people can take and put in. All you need to do is put in a proper Hamiltonian. I think that's probably a slightly better way, from the point of view of maintenance.
Do you have a subroutine which can convert an arbitrary MPS to its canonical form?
Okay. That's also in this. So we have our own ITBD, right? And that's done in that. So what the goal of this library is not to provide everything you need for a tensor network. We want to provide some basic operations, and then you can use this as a building block to build your own things. And but a lot of these idioms. So for example, this is so commonly used. We can just write as some example code, and then people can copy and paste. So
Yeah, just a question. So when you define that these combined operators, this plus and minus, is this combined bonds? What is that doing? This is back. Sorry, this is back on the previous tutorial. 2.1 on the symmetries. Yeah, here. Can we, is there, understand what it's doing here?
Okay, let's just print it. Reset. So basically what it does, so this is without combined bonds.
Yeah.
So I want to combine these three. We want to combine this, turn into a new bond.
Why those three in particular? So I guess two of these indices are kind of the sort of fake ones that just carry that there's a +1 and a -1 for that's plus and that's minus, which is kind of what I traced together somehow.
So what are these?
Well, it's just additional bonds that carry on the numbers.
Yes, I think so.
Yeah.
Right, so they're the ones that have dimension 1 here, I guess, right? Yeah, so 2 and 4.
I think, oh, okay. So I think one of them carries -1, one carries
Right.
+1, and I want to basically
Just
merge
do it
them.
all.
Yeah.
Merge them. Yeah.
So merge them, I get the
Right.
proper operator.
Right.
Yeah, so this is the,
Why is that done as a combined with another bond? I guess.
because combined bond basically just squash them into
Right.
a single index.
Okay, so it wouldn't matter which other bond you combined it
Yeah.
with. Then.
Yeah. So in general, you don't have to. So this is because we know the answer, so
Yeah.
we want to combine this to make it into a tensor like this.
Would it be better to express it as like a trace or something instead? Just like take two indices and trace function, just get rid of those two indices. With them.
But I think that's essentially doing the same thing, just we call it differently because.
Yeah, but then it's okay. I mean, it's just semantics, but it's combining it
Yeah.
into another lake, which seems a bit.
Yeah,
seems
yeah.
a bit-
You mean the
strange.
dimension doesn't look right?
Yeah. Well, it's combining. Yeah, I mean, it's combining two bonds into another bond. I mean, how do you choose which other bond you want to combine it into? You know. What would happen if you didn't have another bond, for example, if it was just a scalar? I mean, if you just wanted to make a scalar out of that, is there a way to do that? I mean, it is
Okay.
it is
I see
basically
what
a
you
trace
mean.
operation, right?
Yeah. We have partial trace and we have trace.
Right.
All this.
Right. So can you express that as a trace?
I think so,
somehow
yes.
It seems more natural to me.
I think so.
as a trace.
Yeah. Because combined bond is actually for other things.
Mm.
Because sometimes you like what I say, you need a fat index. So should I go on to the third tutorial, or again we can talk about what people think about this design. Yeah, this is so basically just an example. It's really doing the 2D tensor network. Okay, so we want to update this paths and using simple update. Okay, so the way we do it is we just use 1D ITBD ideas and maybe in 2D. And as people mentioned in the week, So this is basic. This is not a good update because it's basically updating a tree. It's not really update. It doesn't just you don't update a loop. And this is the simplest 2D algorithm that one can implement. So these are the details. Okay, but let me just explain the way we design the algorithm. Basically, so I just say if I z is equal to 3, I have a b c a b c a b c. Okay, so I should c goes to c. Yeah. So this a b c. So the way we design the algorithm is that we use a simple function, the same function. So basically, we contract something like this, a to a. Okay, sorry, this is a to a. Let's just do this, and b to b, c to c, and then keep rotating. And you have a z equal to 4, then you have a. So basically, you're keeping this update. So essentially, this corresponds to. Let's see if I have a graph here. So essentially, your corresponds to do update here, 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 here. Okay, but with the proper way. So this is how you program to higher dimension. So you can write a general coordinate number z function and just keep doing this. So this is how this is done. Okay. So again, you need a helper function, and so with this complication, so the manipulation of labels becomes very important. Where to insert a label, where to. So I won't go into the details. Yeah, you can look at the code and match it with the label in the tutorial, and you can kind of understand how it works. Yeah, but basically this is the subroutine. We'll just do this thing. This is the main function. Will do this thing, and then as usual do SVD, and you have to permute your labels so that you can go into the next cycle. So let's run this. So this part, so normally a 2D tensor network, you have, for the quantum model, you have two parts. The first part is to get the wave function, and the second part is to get the expectation value. Okay. So it boils down to get the best tensor you can get to describe the ground state wave function, and use this tensor to contract your tensor network to get the say energy of magnetization, so on. So this is the first part. This part of the tutorial is just the first part to get the tensors. So now I have my tensors, and using this local this energy, I can get I can have some energy convergence criterion. It seems to converge. Of course, more sophisticated method, you need better way to compute the energy. Okay, so it converges, and then we want to use these tensors to do the next step. Okay, so the next step is using TRG. So I save the tensors to files. So for later use. So this is the ITP debug. So basically, the idea is just keep doing this. You simulate a 2D tensor network by using the 1D kind of way to update. Okay, so I hope I explained it very clearly how these labels are changed during the process. Because assigning label just basically telling the library which legs to contract. So the second part is doing TRG. So just a brief summary. So basically, we are contracting this double tensor network. So either we have to do this norm. So it's a bracket. So basically, the physical indexes are contracted first. So these are the double tensors. And if I want to compute some order parameter, so then I have some operator here acting on the physical indices, and so this and contract them. So this is like weighted with the matrix element. So this we call impurity tensor. So the goal now to calculate a numerator of this is just to contract this kind of tensor network. Okay. And the TRG way of doing this is just you have AB sublattice, you SVD them in different ways. Okay, make them the rank 3 tensor and truncate, and then you get something like this. And then you just contract this part exactly, and then you have a tensor network like this, and then just keep going until you have only 4 tensors left. You contract them exactly. Okay, so here we first construct the double tensors. So basically, again, the contraction is done by setting the proper labels. Okay, so if you program unit 10 a lot in the future, then you realize that a lot of times you just set the right labels in your operation. Yeah, and we do a combined bound here. Basically, just combine this alpha prime, beta prime. Okay, and we can construct the impurity tensor. So basically, just get the matrix, to get the operator, and then fold it in. We need to do the SVD. So there will be 2 sides. Okay, so A side and B side. Then we do a different SVD and return the matrices. So this is where programming using Unit 10 becomes easy, because all you need to do just read in this tensor network file. Okay. So basically, this will give you the proper network you want to contract. So it will be something like this. Okay, all you need to do is just plug in the tensors. So this contraction is done just with this one line. You put in the proper tensors and then do launch. Yeah, so this is basically some So for example, you just contract the impurity tensors at some proper places. Okay, for example, I want to have yeah, so if I look at my tensor network, it can be one of these. So I have 4 contractions I need to do. One is this. So it'll be identity, sorry. The operator is identity is some impurity tensors. Operator is identity some impurity tensors. So this is describing this in this. And this will give you the renormalized impurity tensors. So this is the renormalized norm. So and then just calculate expectation value. So this is the main loop. So then we can run the transverse IC model. Yeah, so this is going to take a while, but this is looping through different transverse field and getting the energy. So again, 2 parts. One part is to get the tensors, and now it's using a tensor to calculate expectation value. No, this is slow. And if you do it, you'll get a metallization curve like this. What is? I think that's off by 2. So I think I screw up some. So get the 3 point something. Sorry, this should be. Must be something wrong when I construct my Hamiltonian. Sorry. Yeah, this is probably a factor of 2 and a factor of 4. But you understand. It should be 3 point. Okay. So that's it. If you have any questions, then you're welcome to just email me and suggestions or something that you want be implemented, and we're open to collaboration. And hopefully, in the future, some of you will be able to contribute to this platform. Thank you.
You can support us kind of partial SVD.
No.
So you can only support the full SVD.
Yes. So basically, we wrap everything in LaTeX. Recently, we have a wrapper for RPEC. But yeah, then that can be, you can have partial SVD. But that's how we do our line shows. Slow.
Thank you again.
Okay, thank you.